Welcome everyone to lecture number 10 on nonlinear dynamical systems. We will continue with the Bendixson criteria and the Poincare Bendixson criteria. In particular, we will see important examples. One is the Lotka-Volterra predator-prey model and also the van der Pol oscillator. Let us start with the Lotka-Volterra predator-prey model. This is studying how the population of two species vary as a function of time. These two species are classified into prey and hunter. So there is one species that is a prey, another species that is a hunter, and we will study the model of this prey and hunter species. Of course, we are studying a simplified model. Let XH be the hunter specimen in the model and let XP be the prey specimen in the model. So what does this equation say? X dot is equal to X dot H equal to minus X of H plus some quantity that depends on both XH and XP, and X dot P equal to XP minus XH XP. So the first term in each equation is how the particular species would evolve if there were no other species. Yeah. So the first equation says that if there were no prey, that is if XP were equal to 0, then XH would just decrease as a function of time. It would decrease exponentially because there is no food. So left to itself, the hunter species would just decrease. But for each interaction between XH and XP, the hunter eats the prey, and hence the next term, the second term in this right hand side, is causing an increase in the hunter population. So the hunter population decreases because of its own population, and it increases because of its interaction with XP. So the rate of increase is proportional to both XP and XH population. So it is bilinear in the two. It is equal to the product, that is the increase causing term. On the other hand, the prey itself is just going to multiply, it's going to increase exponentially when left to itself if there had been no hunter species, and interaction with the hunter species causes XP to decrease. So quantities XH and XP are all positive, and whether they increase or decrease depends on its own population and also population of the other species. So this is a reasonable model for how dynamics of two species that interact with each other evolves as a function of time. Of course, we have simplified most importantly in the sense that more generally there would be some constants. X dot H would be equal to minus A times XH plus B times XH XP, and X dot P is equal to C times XP. The rate of increase is proportional to some C times XP in general, and the interaction causes a decrease with this multiplication with D. So this is how one could study a general model, but one can consider that we are choosing a different unit for XH and XP so that these constants become equal to 1. Also there is some normalization that has been done so that we are studying this model. So, of course, this itself is a simplification. This model is also a simplification because there might be some higher order derivatives. We have seen already how the population of just one species can vary with resource availability, with the ability to reproduce depending on the interaction between species. All that has been ignored. We have assumed this first order dynamics with respect to itself, and just the product, the interaction is just the product of the two species population. So the question that we can ask for this particular model is, what are the equilibrium points? What is the nature of the equilibrium point of the linearized system? Are there periodic orbits? These are the questions that we will ask. So let us go back to this particular model and we will find the equilibrium points for this system. So d by dt of xh and xp is equal to minus xh plus xp times xh, and this is xp minus xp times xh. Yeah, so this is our f. So equilibrium points points are those values of xh and xp where f1 of xh comma xp equal to 0 and also f2 of xh comma xp equal to 0. So what do we get by equating xh minus xh plus xp xh equal to 0 and xp minus xp xh equal to 0? For a particular value of xh and xp to be an equilibrium point, these two equations have to be satisfied. So let us see what are the values for which these equations are satisfied. First equation says xh equal to 0 or xp equal to 1. Second equation says xp equal to 0 or xh equal to 1. So this gives us how many pairs of equilibrium point? An equilibrium point has an xp and xh coordinate. So let us see what all possibilities are there for equilibrium point. So if both equations have to be satisfied, then one can have 0, 0. Yeah, so this is nothing but xp equal to 0 and xh equal to 0. So the first component in this is xh, species value. Second is the xp, population value. So both equal to 0 is one equilibrium point. That is what we get from here. And both equal to 1, 1, 1. Yeah, so which means xh equal to 1 and xp equal to 1. This is another value for the equilibrium point. You see, notice that this if xh is equal to 0, you cannot have xp equal to 1. Why? Because for the other for both equations, this is equation 1 and this is equation 2. Yeah, this is 1, 2. Equation 1 says that any one of these two possibilities. Equation 2 says any one of these two possibilities. And when we combine them, we get that these two equilibrium points, these two values of xp and xh are situations where the population species does not change as a function of time. So this is where xh, this is xp. So one equilibrium point is here, another equilibrium point is here. This is the equilibrium point 1, 1. This is equilibrium point 0, 0. As I said, the first component denotes the xh value. Let us see what happens if xp is always equal to 0. Xp equal to 0 means this is a hunter population. Yeah. So our dynamical equation system says that if xp is equal to 0, which means that the second term is always equal to 0, and if you put xp equal to 0 here, then xh is just decreasing. That is why we have drawn these arrows. And if xh were equal to 0, so this is sitting on the xp axis, then xp just goes on increasing. This is how the arrows look. But more generally, it is a combination of the two. So for example, let us take what happens at 0.5, 0.5. Let us draw the arrow at this particular point, which corresponds to 0.5 and 0.5. So at xh equal to half and xp equal to half, we get x dot h equal to, so this is just substituting 0.5 in place of these two. So we get minus 0.5 plus 0.25, which is equal to minus 0.25, and xp dot is just 0.5 minus 0.25, which is equal to 0.25. So this is the vector whose xh component is negative but xp component is positive. So this is an arrow that looks like this. So that its xh component, the horizontal component is xh, it is decreasing, but xp component is increasing. So like this we can draw arrows for all the points. One can check that this is how we get. Yeah, let me draw a bigger figure. Only the first quadrant is reasonable because the populations don't become negative. So this is a point 1, 1, this is 0, 0. as I said, XH population is going to decrease if XP is equal to 0. XP equal to 0 corresponds to this XH axis, and XP axis corresponds to XH equal to 0. So, I am sorry. So, XP, when left to itself, the prey population is going to increase. That is why the arrows should all be in the direction of increasing XP. So, the correct figure should be and this is a point 1, 1, and we already checked that at intermediate points, at this point it is like this. Well, if it is a little higher, let us verify this, that this is how it looks. So, this itself is an equilibrium point. If it happens to be at the point 1, 1, if the hunter population is equal to 1 unit and the prey population is also equal to 1 unit, then it remains constant. But for small perturbations about that point, the arrows I have drawn like this, but this requires verification. So, let us take a sample point. This particular point has XP coordinate equal to 1, but XH coordinate slightly more than 1. So, for example, let us consider the point XH comma XP equal to 1.1 comma 1. Yeah, let us see what happens for this particular point. For this particular point, we have drawn the arrow like this, but let us check whether it indeed is like this. So, XH dot XP dot equal to, we are evaluating at the point XH comma XP equal to 1.1 and 1. So, this is minus 1.1 plus 1 times 1.1. So, this is equal to 1.1. And XP population, rate of change of the prey population is equal to 1 minus 1 into 1.1. Yeah. So, this turns out to be equal to XH dot XP dot is equal to, the top component is 0 and lower value is minus 0.1. This is what happens when XH is slightly more than 1, slightly more than equilibrium point, but XP is equal to the equilibrium point value, that is equal to 1. So, when we do this, then we are speaking of this point here. For this point, we are getting that XH rate of change is equal to 0. So, the horizontal component is equal to 0 and the vertical component is equal to minus 0.1. That is why it is vertically downwards. Yeah. So, similarly, one can check for each of these 4 points. What is the property of this point? Its XP population, the prey population is slightly more than 1, but XH population, the hunter population is equal to 1. For each of these 4 points, one can verify and see that the arrows are indeed like this, suggesting that there is a periodic orbit around this point. So, there are periodic orbits close to this, but this point on the other hand looks like a saddle point. So, let us verify this by linearizing the system at each of these 2 equilibrium points. So, let us go back to the dynamical system. So, XH dot XP dot minus XH plus XP XH XP minus XP XH. So, del F by del X. So, this is equal to F1 of X, F2 of X equals this. So, the first row, the first function here is called as F1 of X, the second function here is F2 of X. Del F by del X is equal to a 2 by 2 matrix. The entry here is derivative of this with respect to XH, that is equal to minus 1 plus XP. The entry here is derivative of this with respect to the second component of X, that is XP. So, this is equal to XH. the entry that comes here is derivative of f2 with respect to xh. Here we get minus xp, and the entry that comes here is the derivative of this with respect to xp, the second component of the state. For that we get 1 minus xh. Yeah. So as expected, this is a matrix. This is a 2 by 2 matrix which depends on xp and xh. So we are going to evaluate this matrix at the equilibrium point. So del f by del x evaluated at the equilibrium point 0, 0. This is one of the equilibrium points, and for this particular equilibrium point we get minus 1, 0, 0, 1, and del f by del x evaluated at the other equilibrium point 1, 1, we get equal to, by putting xp and xh both equal to 1, we get 0, 1, minus 1, 0. So we have these two A matrices, one A matrix for the equilibrium point 0, 0, and the other A matrix for the equilibrium point 1, 1. So it's not difficult to see the eigenvalues of these two matrices. So equilibrium point 0, 0 has eigenvalues for a diagonal matrix. The eigenvalues are nothing but the diagonal entries. The equilibrium point 0, 0 has eigenvalues 1 and minus 1. So we already saw that this is an example of a saddle point, and the equilibrium point 1, 1 has eigenvalues. What are the eigenvalues of the matrix? Of which matrix? Of this matrix. Eigenvalues of this matrix are plus minus j. As we noted in one of the first few lectures, that the eigenvalue of such a matrix, if beta is not equal to 0, then the eigenvalue of this matrix are equal to alpha plus minus j beta. Yeah, the eigenvalues of such a matrix are complex. Precisely what complex values are the eigenvalues? Alpha plus minus j beta. The diagonal entries are the real elements, real part, and the off diagonal entries with opposite signs correspond to the imaginary part of the eigenvalue. So these are the eigenvalues even when beta is equal to 0. So for this particular equilibrium point, we have this special case, and so the eigenvalues are plus minus j, which we know corresponds to a center. Yeah, the equilibrium point is what we called a center. So a center is one that has periodic orbits, and we already saw that for this particular plot, indeed this particular equilibrium point has periodic orbits, and this is a saddle point. So the linearized system is a center, which is nothing but a continuum of periodic orbits very close by. Different initial conditions correspond to different periodic orbits. They all correspond to periodic orbits and different periodic orbits. Is that the same for the nonlinear system also? This is the topic that we will see in detail today. So please note that we have investigated the Lotka-Volterra predator-prey model. For convenience, the predator we have called as hunter, so that we can use a subscript h, and the prey we continue to call p, xp. The simplified model shows two equilibrium points. One equilibrium point, the linearized system, is a saddle point, and the other equilibrium point of the Lotka-Volterra predator-prey model corresponding to 1, 1 corresponds to a center after linearizing. So what is important is that this particular equilibrium point is a center. We already saw that these arrows are suggesting like this. If it were a linear system, then when we go close, this is a periodic orbit. When we go close to this and another initial condition, it may or may not be a different periodic orbit. The linearized system says so, but it need not mean for the original nonlinear system also. For example, if these are two different initial conditions, they correspond to the same periodic orbit, but different initial conditions like this may correspond to different periodic orbits or might converge to the same periodic orbit. This is a subject that we will see in detail today. So if all these initial conditions correspond to different periodic orbits, then we will like to say that there is a continuum of periodic orbits. These periodic orbits are not isolated, but very close to each periodic orbit there is another periodic orbit in a very close vicinity. Suppose this is a periodic orbit, the initial conditions starting from here correspond to periodic orbits also. In that sense, there is a continuum of periodic orbits. So it is a very well known important fact that for the particular Lotka-Volterra model that we have taken, let us go back here, for this particular Lotka-Volterra predator-prey model, for constants A, B, C, D, we have two equilibrium points 0, 0 and 1, 1 when you assume A, B, C, D equal to 1, but for a different point when A, B, C, D are some positive constants possibly not equal to 1, there are two equilibrium points. While the 0, 0 is a saddle point, the other equilibrium point is a center, and moreover for the non-linear system, for this Lotka-Volterra predator-prey model, there is a continuum of periodic orbits. This particular fact for this particular model, for any of these two models, is a very important fact, and one can modify this model suitably so that we have isolated periodic orbits. So today we are going to see a different example where there are indeed isolated periodic orbits. So let us use Poincare-Bendixson criteria and the Bendixson criteria to check if there are periodic orbits. Let us see the Bendixson criteria. What does this Bendixson criteria say? We will evaluate this particular quantity and check whether this is identically equal to 0 or not. If it is not identically equal to 0, only then we can go ahead and apply the Bendixson criteria. So let us evaluate this particular quantity for our example. For our example, f1 of x was equal to minus xh plus xp times xh, and f2 of x is equal to xp minus xp times xh. So this f2 we could also call as fp, and this is equal to fh. fh denotes the rate of change of xh and fp denotes the rate of change of xp. So let us evaluate del fh by del xh plus del fp by del xp. When we evaluate this, we get derivative of this with respect to xh is equal to minus 1 plus xp plus derivative of this with respect to xp, we get this equal to 1 minus xh. So this is equal to xp minus xh. So is this identically equal to 0? No, it is not identically equal to 0. Yeah, so it is, that is why we can go ahead and apply the Bendixson criteria. Let us now apply it and see. Xp minus xh, sign of this quantity, if the sign does not change over a region, the Bendixson criteria says that if the sign of this particular quantity does not change on a region, then there are no periodic orbits contained inside that region. So when is xp minus xh equal to 0? It is along this line. So everywhere to the right of this line, this is xh, this is xp. To the right of this line, this quantity is negative, and above this line or to the left of this line, this quantity is positive. So the Bendixson criteria says that there cannot be a periodic orbit contained to the right of this line, nor can there be a periodic orbit to the top of this line. It does not, so this is the equilibrium point 1, 1. The Bendixson criteria does not rule out such a periodic orbit. That doesn't lie entirely in this region, nor does it lie entirely in this region. Yeah? So this is an important property to note, that the Bendixson criteria only says that can such a periodic orbit exist inside this region? No, this is not possible. Can a periodic orbit lie entirely in this region where the sign of this is all positive? That is also not possible. However, this particular periodic orbit could exist. So, Bendixson criteria is only a sufficient condition for non-existence of a periodic orbit lying entirely inside a region. Let us now check what the Bendixson criteria says for a linear system. X dot is equal to Ax, for which the equilibrium point is 0, 0. Yeah. So Bendixson criteria is applicable when, for the planar case, that is when x has two components at each time instant. X of t has two components, x1 and x2. So suppose A was equal to, maybe we see a slide about this. So for the Lotka-Volterra predator prey model, we have already seen this. Before we see another example, let us see this particular case. Periodic orbit for a that is of this form. So our A we have already assumed it is of this form, and now we will do del f1 by del x1 plus del f2 by del x2. Notice that these two terms are nothing but the diagonal entries of this matrix A. So for this particular A, the diagonal entries are both 0, so they add up to 0 also. So they are identically equal to 0. No matter which x1, x2 you check, this is going to be equal to 0. This particular quantity is expected to be independent of x1, x2 for linear systems. Why? For linear systems, for linear time invariant systems, these four entries are all independent of x, and hence you differentiate f1 and f2, f1 with respect to x1, f2 with respect to x2, which is nothing but just picking up these entries, picking the values at these two positions, and they are going to be independent of x. So for this particular A, we get this identically equal to 0. So do we say that Bendixson criteria is not applicable, or do we say that there are no periodic orbits? Of course, we know that for this particular A, the eigenvalues of A are equal to plus minus square root of 2 times A. So if A is positive, then the eigenvalues are plus minus 2 times minus of 2 times A. We will just verify this. So what is Si minus A? Si minus A is equal to determinant of Si minus A is equal to S square plus 2A. So eigenvalues of the A matrix are nothing but roots of the determinant. The roots are square root of minus 2A plus minus. So if A is positive, A greater than 0, then complex, purely imaginary in fact. If the eigenvalues are purely imaginary, then we know for a linear system there are periodic orbits, and if A is less than 0, then eigenvalues are real. One of them is greater than 0, other is less than 0. Why? Because if A is negative, this quantity itself under the square root sign is positive, so we can take the square root, and one is positive, one is negative. So for this case, the eigenvalues are here, and for this case, the eigenvalues are here and here. How far from the origin depends on the value of A, of course, but whether they are, depending on whether A is positive or negative, affects whether the roots are purely imaginary or real. So we know that for this case, the equilibrium point is a center and there are periodic orbits, while for this case, the equilibrium point is a saddle and there are no periodic orbits. So the important case when this is identically equal to 0, that particular case could correspond to either there are periodic orbits or there are no periodic orbits. This is just to see that the Bendixson criteria is unable to say anything when this is identically equal to 0. That is precisely the reason that Bendixson criteria assumed that this is not identically equal to 0, and then you start looking at whether the sign changes or not. So let us take a case where for x dot is equal to ax, let us check what is del f1 by del x1 plus del f2 by del x2. What is the value of this? We will check that this is equal to 4 by calculation explicitly. So x dot equal to ax means 2x1 plus 3x2, that is the meaning of a acting on x, and the second row of a will be used to multiply with x to get minus 3x1 plus 2x2. So when we do this, then we differentiate the first component of x dot with respect to x1 and we get this equal to 2. We are picking up just this entry, and the second component of x dot, that is f2 of x with respect to x2, we are doing this. So notice that derivative of this with respect to x1 is just this component, this first 1 by 1 entry, and the derivative of this with respect to x2 is just this entry. That is the reason that I said that doing this particular, to evaluate this quantity is nothing but to add the diagonal entries for a linear system, for a linear time invariant system. So we get this equal to 4. This is greater than 0 and it is independent of x1, x2. For linear systems, we expect that this will not depend on x1, x2, and it is indeed independent of x1, x2. Since it is greater than 0 for all x1, x2, we get that no periodic orbits. No periodic orbits in R2. In the entire state space, in the entire plane, there are no periodic orbits. So for linear systems, we can check that as long as the diagonal entries don't add up to 0, as long as the diagonal entries don't add up to 0, this quantity will not be identically 0, and then we can see that periodic orbits are ruled out. When would periodic orbits be possible? If the diagonal entries add up to 0. If the diagonal entries add up to 0, we cannot say that the periodic orbits exist, because the Bendixson criteria is silent for that case. It does not say anything when the diagonal entries add up to 0 identically. We already saw that it is possible that there are periodic orbits. It is also possible that periodic orbits don't exist when the diagonal entries add up to 0. So this is already the complication for linear systems. So for the Lotka-Volterra predator-prey model, to show that there are periodic orbits is a difficult thing, and it is an important research topic, after which it has been concluded that there is a continuum of periodic orbits for the particular model that we studied.